class, good evening. This is the assignments problem solving session of course electronic theory of solids. 2026, as you know, offered by NPTEL. And in today's class, the problems which I'll be discussing will be of the superconductors and the order parameters. So, superconductors, as we know, the one which has the zero resistance and the diamagnetism, the perfect diamagnetism, and these are the properties which we know. But there are critical temperatures, there are critical currents, all those parameters, and how to estimate them. I'll be discussing in this assignment. So, having said that, let me start with a very basic question. So, the question which I will phrase is. The question is the superconductor. Let's say the superconducting transition temperature of lead, which is a superconductor, of course, we know is 7.26 Kelvin, and the critical magnetic field at 0 Kelvin is, let's say, some number. Then we have to estimate the critical field at a given temperature. So the idea is, like, if you have a superconductor, then it is there is a critical temperature and there is a critical magnetic field. Why they are called critical? Because if you go above T greater than Tc, there is no superconducting state, no superconductor, and below Tc, superconductor. Then there is a critical magnetic field also. If your magnetic field is greater than B critical, then you won't be having any superconductor, because that magnetic field then kills your superconductivity. Okay? And if your B is less than BC and your T is less than TC, then you will be having superconductivity. But now, let's say if you are at temperature T1, right, then your BC1, B critical one, will be different. Will be BC, let's say T1, because it's a function of the temperature. So let's say if I write the question which I said, so you will understand from this problem that if you change the magnetic field, the critical temperature till which your material remains superconductor also changes. So it's not a very linear function. It's not a linear function, but I'll come to the form also. What is the form of this critical temperature and the magnetic field? So let's say the superconducting transition temperature of lead is 7.26 Kelvin, and the critical magnetic field at T equal to 0 Kelvin, which is absolutely not possible to reach experimentally, because you can't achieve the 0 Kelvin. Because thermodynamics, uh, you'll need enormously large power to go towards the 0 Kelvin, and then of course you won't be able to put that much of power to go to 0 Kelvin, and the entropy limits that one. So let's say, but this is the critical magnetic field given. If you take the curve and fit it and take it to 0 Kelvin, you get this number, maybe 64 into 10 power 3 material universe, and the critical magnetic field question asks us to derive at 5 Kelvin. So first we'll have to note down the parameters. Okay, what are the key parameters in this question which we should think of? So let's note down the. So this is the key step to solve any question. If you just write down the parameters from the question and then think what is the formula which relates all those two questions, then you will be able to use the formula to extract the third quantity. That's the main goal which goes into solving the numericals. But to see the physics, you should know the concept behind it. So the critical temperature TC at, of course, zero magnetic field is 7.26 Kelvin, and the critical magnetic field is also given. Generally, the temperature changes. Okay, I should not write. Uh, I should write the beat till which a superconductor will be there. So the critical term we define when we take either if temperature is zero, then the magnetic field we call the critical. If the magnetic field is zero, then the temperature till which it remains superconducting, we call that also critical. So that's the convention generally used, but the temperature till which material remains superconducting do change with the magnetic field, as I said earlier. So these are the critical temperature and the critical magnetic field. Now, if we look at the relation, so following the relation as derived in the class, following the relation between T temperature, Tc critical temperature, at zero critical magnetic, at zero this critical magnetic field, and Hc till which it remains the superconducting is Hc is equals to H0. Okay, I should write it. T temperature of material TCH note I already defined. Hc is magnetic field till which material remains superconducting. Of course, at temperature T. At temperature T. I'm sorry. Hc goes as H naught 1 minus T over Tc square. Yeah, 1 minus T over Tc square. So let's just substitute the values because we have to estimate this Hc at temperature T equals to 5 Kelvin. So T is equals to 5 Kelvin. This is also given. So we'll just substitute the values to extract the value Hc. So Hc is equals to H naught, which is given as 64 into 10 power 3 1 minus your temperature T is 5 Kelvin, your Tc critical temperature as given is 7.26 Kelvin square Hc is 64 into 10 power 3 times 1 minus 5 divided by 7.26 square will be nothing but around it will be 5. Let's do the calculation. 0.474. Yeah. 0.474. And if I subtract it out of 1, it will be 64 into 10 power 3 times 1, 0.525 or 526 if I just approximate. And if I just do the calculation multiplied with the 64, it will be around 33.64 into 10 power 3 inverse. So this is the temperature till which this is the critical magnetic field at temperature T equals to 5 Kelvin of lead. Okay, this is about lead. Let me ask you one thing. Which is the first material? Which is the first material in which superconductivity was observed? Yeah. Anybody? Which is the first material in the world in which the superconductivity was observed? Helium is superconducting, right? Helium is superfluid. Helium is superfluid. It's not superconductor. I mean, they are two different things, right? I mean, helium is superfluid. The first superconductivity, where it was discovered. Superconductivity is something like which has the zero resistance, right? And that shows the diamagnetism. Helium helped it to realize the superconductivity because since people had the helium, they discovered how to liquefy the helium. So they used the helium to cool down the temperature to reach the critical temperature to see whether it's really like superconductor or not. So as you know, if I plot the resistance, okay, this is an interesting story which you guys should know. So this is resistance versus temperature in Kelvin. So generally, it, it's like a metal, right? If you decrease the temperature, your resistance decreases, and then suddenly a point comes after which the resistance goes absolutely zero, and this is known as TC, critical temperature. After this, below this temperature, resistance is zero, and above this, your temperature is uh, your material is metal. In this case, it's metal. Here it's superconductor in this regime. So, so what? How helium helped to derive it was people the first realized it in mercury. So, in I think if I am not mistaken, it was in Leiden University. I think it was around 1900s, maybe I think 1910 or 11. I don't know. You guys can check it. So, it was in Leiden University. So what the student was doing was to measure the resistance of this mercury. They were just measuring the resistance of the mercury. And what they observed was suddenly the resistance went zero. And since before that there was no such observation, no superconductor existed before 1911. And now all MRI machine, whatever you see, MRI machine basically works on superconductors, superconducting magnets. Otherwise, MRI would not have been possible to human being. And nowadays we know how important an MRI machine is. So they were doing the experiment, and what did they realize is, like, if this is your material, let's say this is your mercury, Hg, and they were measuring its resistance. So they were measuring between these 2 points, A and B, resistance. Generally, people do 4 probe, so C and D. They were measuring between C and D the voltage drop. And what they observed was, so through these 2 points, they current source it. This is 4 probe measurement, and this is the voltage. And what they observed was that voltage was zero. Suddenly, your resistance curve was like this, finite resistance, and then suddenly it dropped to zero. And it was surprising to them. Theory came later. Initial was the experiment only. So the experimental results tells us that whether something is there or not, and later the theory comes. So this is your resistance. This was possible only because they kept this thing, as you said, Mansi, helium. So they kept this thing, this whole assembly, at least the mercury part, into the helium liquid bath, and temperature of helium liquid bath is 4 Kelvin. Since people figured out how to liquefy helium, they reached to the temperature of 4 Kelvin, and the critical temperature of mercury is 4.2. This Tc is 4.2. So they were below this temperature. That's why they could see that there is a superconductor. That's why, as you said, first material in which superconductivity was observed is mercury, Hg, and first, and this was possible because of helium. This was possible because humankind learned how to liquefy helium. How to liquefy helium. So, if you liquefy helium, you need a temperature of 4 Kelvin, because above 4 Kelvin and 1 atm, helium is gas. Below that only, it's a liquid, and if you go below around 2.2 Kelvin, it's superfluid, not superconductor. It is superfluid. Superfluid has different property than the superconductor. Superfluid is like something where you form this Bose-Einstein condensate, and in the condensate you have this your viscosity uh, basically goes to zero, and whatever disturbance you provide at one end in your solution travels infinitesimally, like instantaneously, to the other end, because your system is, now you can think it like a braided system. So what information travels at a very fast speed in that case, and information means the disturbance whichever you provide, and that's why it boils up instantaneously if you provide any disturbance above 4 Kelvin, where it's not superfluid. Below that one, it's a complete system. And if there is a hole in your system, let's say superfluid helium. So helium, if you put the helium into the, let's say this is your beaker, and somehow you isolated it from the environment, and this is filled with helium at 4 Kelvin. Then, and there is a hole here, so only some bit of gas will come out, nothing more than that. But if you have the same setup, remember, from this hole liquid is not coming. But if you have the same setup, and if you go below 2.2 Kelvin, you will see the helium will keep rising on the walls. It will, because it has zero viscosity, right? It will rise on the wall. This liquid will travel, and through this one it will come out. The liquid will come out. This is because superfluid effect. Superfluid effect. So helium is a superfluid, not a superconductor. First material it was discovered was mercury, and nowadays we know there are many materials, many alloys in which superconductivity is there, like mercury is there, aluminium is there, this NBSC2 is there, niobium is there. All these things are there. All those materials are there with the superconductivity is there. And now people are trying to bring this temperature Tc somehow to at least the liquid nitrogen temperature at so that liquid nitrogen temperature is 80 Kelvin, because nitrogen is easy to liquefy than the helium. If that is possible, then you would see that in every small hospital you will see an MRI machine, all those things, fascinating things you will see there. Nowadays you don't see MRI machine, all those big machines in every single hospital. The reason being they are very costly. Helium is very expensive. In you can't have helium in your air because it is light and it will go away. It will basically rise and it will escape the Earth's atmosphere. So whatever helium comes from the either the byproduct of some reaction or trapped helium in some regions. From there only these mining company extracts and they give us the helium, and that's from there only the MRI machine, all those things works. So this is about the helium and the superconductivity. I think I went off the topic, but I think this was important to discuss that how was the first superconducting material discovered, and later the BCS theory came. You can read about the BCS theory. You know, these people are still alive, and they got the Nobel Prize for this one also. I think, yeah, I think so. So this is about it. Now let's move on to the next question, which is question number 2. Which of the following? I'll give you option and you will have to say which of the following is true for a superconducting state. So the first option is a superconductor in the superconducting state T less than Tc exhibits perfect diamagnetism, that is chi is equals to -1, right? For diamagnetic material, this paramagnetic susceptibility is, as you know, it's less than 0, and for for diamagnetic is less than 0. For paramagnetic, it's greater than 0. Yeah. So this is SI units, of course. Is option 1. The second option is the entropy in a superconducting state is higher than in normal state. Third, the critical temperature Tc is inversely proportional to 1 by m, where m is the mass of an isotope. And the fourth question is Fourth option is the relative permeability mu is 1. So this covers actually the key concept of a superconducting material, right? If someone asks what is a superconductor, if you answer these four of the options, then more or less you know about the superconductor, at least the basic nature of the superconductor. So let's see. Uh, uh, for option one, two, three, and four. Okay. So what about option A? Option one basically, is it true or false? Anybody? Okay, yeah, option one is true. Nancy, you're correct. The reason being, it's that if you know the famous Meissner effect, right? If you have a superconducting material and you apply a magnetic field below the critical temperature, what will happen? your your magnetic field lines will cannot thread through your superconductor, right? And in that case, they will have to your your superconductor will repel those lines. And what does it mean? It means your magnetic susceptibility is like of the diamagnetic material. And since it's a superconductor, right, it can arrange these your charges such that it can repel the entire magnetic field because of this order parameter, the system, and that leads to internal zero magnetic field, right? And that's why this option A is true. So let me just write down this solution. One is true. Reason, your m is equals to chi h, right? And from the Meissner effect, a superconductor expels the magnetic field lines. And because of that, your magnetic susceptibility chi is equals to minus 1, and your internal magnetic field becomes 0 because your m is like minus h, and there is a positive. Okay, this is, you think it like you have a superconductor in which you are applying a magnetic field P, let's say H, let's say you are applying H, you are denoting it as with H. So what will happen if you apply these magnetic field lines are there, right? So they will bend and will pass through nearby like this, and then again on the top they will become like this. Maybe it's the third one. Yeah. So they will go like this. There will not be any magnetic field threading through your superconductor. This is superconductor, and this is known as Meissner effect. So that basically your internal magnetic field in your system is zero. In your superconductor is zero. So option one is true, that a superconductor in the superconducting state. This is important. Your temperature has to be less than Tc. If your T is greater than Tc, then magnetic field line can pass through your superconductor, because now it's not. Then it will not be a superconductor. Then it will be like a normal metal, right? Below T equal to Tc only, there will be perfect diamagnetism. What is diamagnetism? The one which repels the magnetic field, right? And this is what it's doing. And with chi equals to minus one. Now, what about the second option? Is it true or false? No, no. It's not like no randomness. Randomness is there, but it is less. Second is false. I agree. The entropy in a superconducting state is higher than in normal state. Yes, correct. That entropy in the superconducting state uh, is lower than the normal state. That much is correct. But it's zero, that's not correct. Because randomness is still there in the system. You don't have absolutely zero randomness. It is more ordered because you form the Cooper pairs in the system. So, and now it's in a condensate state kind of thing. You can think it like that, right? But it's not that the entropy goes down completely zero. Some randomness still remains. So let me just then answer it. The second one, as you correctly said, it's the second one is false, correct. But the reason which you gave needs correction. So the Mansi, as you said, it's false. It's that much is true. But the reason, let's just discuss it slightly more because I think that's an important thing to be known that in the superconductor, your entropy is not absolutely zero. So if you take normal metals, in normal metals, your electron moves randomly, right? Electron moves randomly. That means uh, more available microstates, more available states, and if there is more available states, there are more randomness in the system. What that means? It means larger entropy. Because that's what entropy means, right? The randomness. Entropy is a measure of the randomness. And now let's discuss the same material which goes superconducting. So in superconductor, let me write. You have these what we call Cooper pair, right? Electron form Cooper pair. At least this is what we understand from the BCS theory. Electron forms Cooper pairs. Uh, BCS theory concept. And these pairs condense in a single coherent quantum state. So now you have a single coherent quantum state. That means they maintain their phase while traveling. That's what the coherence mean, right? And these pairs condense into a what we call the superconducting state, single coherent quantum state. That what does that means if there is single coherent quantum state? That is less random compared to the electron moving randomly. And what does that mean? It is a much ordered state, much more ordered state. If it is much more ordered state, then that means lower entropy. Superconductor has lower entropy. Normal metal, normal metal has larger entropy. And our option 2 says opposite. It says entropy of superconducting state is higher than in normal state. Whereas the true is in the superconducting state, the entropy is less compared to the normal state. Is it clear, the class? If it is clear, uh, then we move on to the next option. Otherwise, we can discuss it more. Yeah, I don't see any response. Do we? Do I need to discuss it more? Okay, if there is no response, then I will I'll move forward. Option third. Yeah. So what about option three? The critical temperature Tc is inversely proportional to your m, where m is your mass of an isotope. Is it true or false? No, no, no. It is not directly proportional. Okay. So no, no. Is it true or false? Okay, let's first discuss. It's true or okay. Okay, you are saying it's false. That is true. That it is false, but the reason is not true. Option three is false, but the reason is if you look into the class notes and see the isotope effect, right? The isotope effect of isotope effect of superconductors. You realize that your critical temperature T is inversely proportional to square root of m, not inversely proportional to m. It will be square root of m, and because of this single reason, since it's not proportional to 1 by m, it's 1 by square root of m. So that's the reason it is false. So your response was correct, but your the reasoning could have been like reasoning was uh, was slightly off. So this is about the isotope effect. So isotope means, let's say if a material X is there, right, and it has two isotopes, let's say X1 and X2, then uh, they can be superconductor, right? The both can be superconductor if they are, but the critical temperature will be inversely proportional to the mass of M1 and mass of M2. So if you know your critical temperature of one isotope, you can estimate the critical temperature of the another one, right? By taking the ratio, like for example, if you take T1 by T2, and I somehow measured the one material, then for the another one I can just directly calculate, right? Let's say T1 I can calculate if I measured it for T2. So that's the use case of this isotope effect. Okay. If this is clear, then let me ask the final one. Is the relative permeability mu is equals to 1. Is it true or false? Yeah, I think someone is typing. Yeah. So let them finish. Okay. If there is no response, then okay, let's then derive it. If no one knows whether it's true or false, then I would say that let's go and derive it. So the magnetic field, let's derive the relation, and uh, well, let's see what turns out to be, whether it's true or false. Let's just derive it. है ना? So the magnetic field inside the superconductor B, as you all know, right, is you can write to be your mu naught, right, and then H plus M. So this is your magnetization and this is your magnetic field which you apply. So these are the two things, and this is your magnetic field which is passing through your superconductor. And we know that, right? M is equals to chi times H. Like whatever the magnetic field you are applying, the magnetization is proportional to that, and chi is the prefactor, right? Let's just substitute it in this equation. If you do so, what will you get is mu naught H plus chi H. B is equals to mu naught 1 plus chi H. Right? If you see here, I can write it like B is equals to mu, and as it's given here, the relative permeability mu R, right? Mu R times H. That's how I can write, right? So the first response can be very easy. The magnetic field inside the superconductor is zero, below critical temperature. So since H will not be zero, I'll be applying the magnetic field. Mu R has to be zero. That's one thing, right? The another thing can be, as you can see, mu R is nothing but mu naught times 1 plus chi, right? And chi we derived to be minus 1. That's what we said in option A, right? What does that mean? That means that your mu R is equals to 0. And your option says that the relative permeability mu R is equals to 1. That means it is false. Is this clear? Is this clear to the class? Okay, fantastic. If this is clear, then you know the superconductor. Right? You know it's not just zero resistance, because whenever people say that in superconductor, they say, okay, this zero resistance. But not every zero resistance means it's a superconductor. In quantum hole also, you have your zero resistance, but that's not a superconducting state. That's a topological insulator state. So the states are different because here your superconductor shows perfect diamagnetism. It has zero resistance, right? It has more order state because the state collapsed to the one state, Bose-Einstein condensate, right? And you have these Cooper pairs. And then you have the critical temperature, which goes inversely of square root of mass, isotope mass. So if you know critical temperature of one material, you can of one material basically you can tell the critical temperature of its isotope, which has different mass. So the idea is lighter the material, larger the critical temperature. That's what it tells, right? For a particular isotope. Of course, there will be prefactors, but for a particular material with which having isotopes, this is the case. Lighter it is, larger the critical temperature. And as we know, the relative permeability for the superconductor is also zero. The reason being it expels out all the magnetic field. If you see here, it expels out all the magnetic field, and that's the sole reason your relative permeability mu r is zero, because B magnetic field inside is zero inside a superconductor below critical temperature. If this is clear, then I will move on to the next question, which is sorry. In a superconducting state, in a superconducting state, rho is resistivity, right? E is your, of course, electric field, and B is magnetic field. In a superconducting state, if rho is the resistivity, E is the electric field, and B is the magnetic field. What are their values? What will be their values? Below less than Tc, critical temperature. Anyone who wants to tell the answer? This is something I have already discussed. So I would expect the class to answer this one. If not, definitely I would answer, and that will help the discussion go forward. And you guys will learn something from that also. So if anyone knows what will be the answer of the raw electric field and the magnetic field in a superconducting state, please put your answer in the chat. That helps us keeping the session engaged. Sorry, I'm really sorry. 0 for resistivity and magnetic field. And what about the electric field? E. Okay, then let me ask you one thing. You guys know everything actually. The reason being you just are not confident enough to answer the things. That's what I feel. Right? So you should put forth your idea of the physics, whatever idea you have in your mind. Just put forth irrespective of whether you are true or whether it's correct or not. That's a different thing. But with a proper reasoning, if you put the solution, like because the superconductor has the zero resistivity because it's a single state, single condensate state because the BC is theory. It expels the magnetic field will be zero, and you should write their reasoning also because the Meissner effect. It expels out the magnetic field, and then there will be zero electric field also. And this is something which I would expect you guys to answer because yeah. So what is the Meissner effect? Okay. So if you have your superconductor, let's say, okay, this is something which is interesting, and I discussed it also. I think you joined later in the class, but I'll just go here. This part, if you see, this is the Meissner effect portion which I discussed. So, I'm really sorry. I'm having some severe cough. Yeah. So, this is the phenomena, like if you see this Meissner effect. So, if you have material which is can host the superconductivity and you cool it down below your critical temperature T less than Tc, right? Then what will happen? The magnetic field inside the system, right? If you have your okay, let me draw it inside. You have your material. Let's say this is your material X, and you this is a temperature T greater than Tc. So if you applying a magnetic field, what will happen? A magnetic field line will pass through the metals, right? They can pass, right? Nothing stops them passing through the your material. Yeah. So this is your this is in case of the normal metal. Some bit of the magnetic field will pass through your material, right? But if you cool it down below T less than Tc, where it is in a superconducting state, right? So the magnetic field inside will be zero because the magnetic field line will be pushed out of the material, and they will be pushed out, and your magnetic field line will go like this. They will of course not intersect each other, so just forgive me for my drawings, but they will go like this. These are pretty funny negatives. Let me just draw them. Superconductor is a perfect diamagnetic, and this effect is known as the Meissner effect. Of course, on the name of the person who discovered it. So I think it was some a scientist named Meissner. I think Walter Meissner. I don't know. You can check the name. And of course, some bit of it penetrates, and that you the magnetic field penetrates basically also. Some bit of it penetrates, and the penetration. Then there are these penetration length. All those things are there. If you go in the details of this. So basically the Meissner effect, and then you can classify the your superconductor as uh, type 1 and type 2. In the type 2, basically what happens, your superconductor forms these vortices. You can think it like to expel the magnetic field, it develops these rings in which these tiny magnets kind of thing, and through these the magnetic field threads out, and this is what you call the vortices. So there will be partial penetration in type 2 superconductor, and in the type 1 there will be complete expulsion. So there are two type of basically superconductors are there. This is something if you go in the detail of the superconductor. This is something you can read also. And if any question, we can discuss also. Yeah. So I should not deviate from the main question, which is in a superconducting state. Yeah, since here we address this B equal to 0 magnetic field, of course. And if you look at the resistance curve, as I discussed earlier also, if you have your resistance curve goes like this, and then suddenly your temperature drops and it goes to 0 Tc. So below T equal to Tc, below T less than Tc, your resistance is 0. Right? So resistivity, if resistance is 0, then resistivity is also 0. Right? Now the second part, magnetic field. We learned from the Meissner effect that below T less than Tc, till the state is superconducting, your magnetic field B inside will also be 0. So we know the answer of 2. Let's see the third one. So if you see here, okay, what does it mean to have a superconducting state? Okay, let's say you are having at this point and this point. What is electric field? If I ask you, what is electric field? If their electric field is there, then there will be a potential difference, right? That's what we know. Uh, V is equals to minus Ex. Right? Basically, if between 2 points, if electric field is there, let's say these. Okay, let me add an extra phase here. Then I will be able to convey my idea better. Okay. Let's say this is your plate A and plate B, and there are electric field lines here. Right? These are the electric field lines, 3 electric field lines which I have drawn. So potential at these 3 points, let's see, is potential at this point, uh, yeah, and potential at this yellow point. This is the red point, and this is the yellow point. And let me just write that the distance is x. Right? Distance is x. So the put, and let me just write it is VA and VB, these 2 points. Yellow as VB and red as VA. So delta V will be nothing but minus E times X, electric field times X, right? That's what we know, right? VB minus VA will be nothing but minus EX, or I can write VA minus VB is equals to EX. This is the form. Do you guys agree with this one? Are you guys with me till this equation? Because from here only I will derive that what will be the electric field value. Okay, fine, perfect. Now let me just choose the same point A and B in the superconductor. I can also choose 2 points, right? Okay, this is my again A red point, and this is my yellow B, and we know that resistance between A and B is what? As you guys only told me, right? It's zero for superconductor. If resistance is zero, what is resistance? Resistance is VA minus VB divided by current, the current which I am passing through the sample to measure it. And what does it tell me? It tells me that VA minus VB is nothing but 0. Okay, this is my equation number 1. This is my equation number 2. If I substitute equation 2 into 1, what will I get? Ex equals to 0. And what does it mean? E is equals to 0. So in a superconductor, your resistance is 0, your E is 0, and your B is 0. You don't need an electric field to derive, to basically move, to make the motion of the electrons in a superconducting state. That's what it means. And B is 0 because of the Meissner effect. Are you guys with me and are you guys with me on these equations? And if you have any question on these, please ask in the chat box. Is this clear? At least these three relations, because this is something which are very important about the superconductors. That your resistance is 0, electric field is 0, electric field we derive because we know the resistance is 0, resistance is nothing but, if I use the Ohm's law, V by I, V is equals to IR, then that gives me VA minus VB is equals to 0, and that is EX equals to 0 and electric field is equals to 0. If this is clear, let me know, then only we'll move on to the next question. If you have any doubt or question, please do ask. I'm really sorry, some bit of construction is going on nearby and I can't just have control over these things. So there can be some drilling sounds, and those things can be there. Please forgive me for that. This is clear, then okay, let's move on to the next question, which is of course based on the isotope effect. This one, isotope effect. Let's take one question from the isotope effect so that you guys know how to approach this kind of problem. So, 1 second. Sometimes it hangs. Okay. So the question which can come out basically, I will take mercury because that's the first material in which it was discovered. So let's take a question for mercury only. So this question is the critical temperature of mercury with isotopic mass 200 mu 5 Kelvin. What will be the critical temperature? What will be the critical temperature if the mass changes to 205 mu? So let's solve this problem. Since simple isotope effect, nothing fancy. So let's note down the first thing. M1 is given to be 200 mu. T1 is given to be 5 Kelvin. T2 we need to estimate, and M2 given is 205 mu. Since we know that this critical temperature goes inversely of square root of m, so sorry. So let's take T1 by T2 is equals to square root of m2 by m1, and we have to estimate T2. So T2 will be nothing but T2 is equals to T1 times square root of m1 by m2. T1 is what? 5 Kelvin. Square root of m1 is what? 200, and m2 is 205. So this gives you T2 equals to 5 times, let's calculate, 200 divided by 205. 200 divided by 205, right? And square root of it, 0.97560 will be 0.9518, 0.9518. This T2 will be times 5 Kelvin, it will be around 4.76 Kelvin. So here critical temperature changes from 5 Kelvin to 4.76 Kelvin. I think so. That's should be the so you guys can check it also. I think that's what it should be. So 200 divided by 205 multiplied by 200. Okay, I squared it. I should take square root. I see this is not correct. Once again, 200 divided by 205 raised to power 0.5. Yeah, it should be point. That's why I thought this is large change. This much change does not happen. My next solution is 4.94, because if this small most change, if this is change is happening, then we are merely too lucky. It's 4.94 Kelvin roughly. So that's how you calculate the critical temperature for a different isotope. Isotope is something which has the same atomic number but different atomic mass. Uh, is this question clear? That if you are given with, because these are the type of question which might appear in your exam also. That given the temperature, given the mass, and estimate the critical temperature T2, or estimate the critical, or estimate the um, basically the isotope mass if any three parameters is given. All those questions might show up in your exam also. Yeah. If there is question to it, please type in the chat box, and we will take, I think, one more question before we conclude the class. So, if there is No question, then I'll take the next question, which has its four subpart. So actually four questions will be there inside, but there will be small part of it will be there. So we'll just try to get it finished on the before the time or on the time. So which one of the following, or which of the following, actually I should ask, which of the following statements regarding superconductor is false? The first question is, the first option basically, magnetic field enters in the form of flux inside a type 1 superconductor. Yeah. So is this true or false? Correct. So this is the response I would appreciate also. So if it is false, the reason being because the magnetic field passes through only type 2 superconductors, and that too in the form of these quantized flux actually. So that's something which I appreciate the form of the answer also. So the answer is false. This is false, and the reason is, like as you said, that in type 1 superconductor, in type 1 superconductor, complete Meissner effect is there. Is there? That means expels all magnetic field, all magnetic field up to at least critical magnetic field up to critical magnetic field, up to critical field. But in type 2 superconductor, magnetic flux enters in the form of quantized flux or quantized vortices. Basically, the vortices they form. So it's a quantized flux h bar by 2e. And 2e comes, the 2 comes because the Cooper pair. The form of 1 plus and quantized vortices. So this became false. Okay, let me just put then another option also. So the another option is the London's equation is given by of course, current density J is equals to minus n E square by mc times the magnetic field B. So I, this you would have seen in the class. The form might would have been slightly different. In the the London equation is actually is curl of J is equals to minus B by mc. But if you take an this what you call, if you use this convention of the Gaussian units, it's just a the, it's just a matter of a units, like the units which you use, right? So in Gaussian units, J is minus n e square by m times if you take the curl of J, that will be minus n e square by mc times m. So this is this do matches with the given option. So this is true. This is electromagnetic potential A. Electromagnetic potential A. So this is in Gaussian term. So if you take curl of J, so curl of A will be nothing but magnetic field. That's where this equation comes. If you are slightly confused, then this is in the Gaussian units. Your curl of A will be B, curl of J will be curl of J, and that's where this equation comes from. Yeah, and I think we'll keep it to be this much only, maybe for the today's class. You know, today's we'll end the session with the these many concepts of the superconductors, because this is this otherwise this will be too much to digest, right? So I'll keep the stuff to be of this much only, and will advise you to at least will ask you guys to recall these concepts. Meanwhile, in this week, so just go over it once more. So what about the superconductor, critical temperature, critical magnetic field, right? Then how to estimate this formula. You must remember, this is very important, not only for your exams. In exam it will definitely show up, right, most likely, but for your concepts on the superconductor, so always be handy with the formulas, right? And then uh, when the first superconductor was discovered, I think 1911, Leiden University, mercury was the first material in which was observed. This was possible because people could liquefy helium. So they went below critical temperature of 4.2 Kelvin, and below 4.2 Kelvin they could see this superconducting, that resistance going to zero. Then we discussed of the helium also, because there was one misunderstanding about superconductivity and superfluidity. So this is something also we discussed, superfluidity of helium below temperature of 2.2 Kelvin. Then we discussed about the superconductor, its Meissner effect, its entropy, how its entropy is different from the normal state, what the isotope effect, how your critical temperature is dependent on the isotope mass, the relative permeability. This is something we derived here in this section. Then moving forward, like we derived the electric field, the magnetic field, and the resistivity relation inside a superconductor, right? Using this relation, and we proved that rho equal to 0, E equal to 0, and B equal to 0 superconductor. Then someone asked about the Meissner effect. We had discussed then the Meissner effect below critical temperature, how the superconductor behaves, then type 1 and type 2. And in the next class, I will ask you, okay, this is take an assignment type maybe. So give me examples of type 1 and type 2. Okay. So this is your assignment time you can think of, right? Uh, two materials which are type 1, and two materials which are type 2. It is something which I will ask you in the next class. So uh, keep these one ready. At least read about these two materials. Read about these two types of superconductors and the two materials which poses these two, and where should aluminium lie? This is the third question. Where should aluminium and mercury lie? Will they be type 1 or will they be type 2? How would they lie? Or NBSC2 also. Right? These three material I'll ask other than these two questions. Then we use the isotope effect to estimate the critical temperature of an isotope of mercury. Then we discussed about which of the following statements regarding superconducting is true, whether the magnetic field enters into superconductor or not, what is the London's equation, right? All those things. The equation which relates the current density and the magnetic field basically, right? So this is something which we discuss in the class. And if you have any question or doubt till this point, please do ask in the comment in the chat box, right? And if there are no questions, then we will conclude the class. Okay. Then if there are no questions, so let's thank the class for being here and okay. Uh, Thank you guys for being in the session and being so attentive, being so responsive because it helps me at least to keep the session engaging. And the feedback, of course, do help me to keep the lines on track. Otherwise, I might go off some of the track and you guys will not understand all those things. So, thank you for being responsive. And with this one, I will take your leave. Bye bye. We'll see you on the next session, maybe on the Saturday. Till then, enjoy.